So while everybody else is logging on, I'll introduce myself. My name is Matt White. I'll be your host and moderator today. I've been with Quantcast for 8 years, and today I serve as our Vice President of EMEA. Our goal today is to answer questions such as, what is machine learning? How do computers recognize patterns in the real world? How does operationalizing simple tasks make room for marketers to nurture creativity and strategy? There will be about 45 minutes of presentation and 15 minutes of Q&A. Please do register your questions as the presentation is going along. I really look forward to a rich discussion post-presentation. That's what's happened when we've run these webinars before. For those who aren't as familiar with the Quantcast or haven't had a chance to meet with one of our commercial teams lately, Quantcast is an audience intelligence and measurement company headquartered in San Francisco, combining machine learning, a privacy by design approach, and live data drawn from more than 100 million online destinations. Quantcast provides software, information, and advertising services for marketers, publishers, and advertising agencies worldwide. Today, we are in 10 countries and we have over 20 offices. A little bit about Peter before we get started. As Chief Technology Officer at Quantcast, Peter is responsible for the development of products which allow marketers and publishers to make smart choices as they are buying and selling effective advertising. Peter is a very enigmatic speaker, and so on that note, I will push it over to him. Over to you, Peter.
Thank you, Matt. And hello, everybody. I'm afraid it's a little bit early here in San Francisco, so if I look a bit bleary-eyed, that's why. And hopefully you'll get to see the sun come up on my face during the next 45 minutes. All right. So before we get started, a bit about me, so you understand why I'm talking about this subject. I was born, as all of us were, way back in 1980. March 10th, if anyone wants to send me a card. My 40th was rubbish this year. I was originally an academic. I worked in a field called machine learning before it was cool. I used to be a university lecturer at the University of Liverpool. I then spent the majority of my career in financial markets, largely because when I sold out from academia, it was the industry that was paying the most, so with my skill set. Then I got really bored and frustrated in financial markets. At the time I was working as head of risk and pricing over at UBS Investment Bank, and wanted to get back close to machine learning again, and joined the glamorous world of media and advertising when I joined Quantcast about 4 years ago. And my hope back then was that I could make my day job closer to what I did in academia, which was machine learning. And so that's what I've been doing since then. And as Matt said, now I'm CTO here at Quantcast, taking care of how we apply this kind of technology in our world. So why am I talking about machine learning a lot at the moment? I've been doing this for probably 18 months now. And it's really because we're in this kind of massive hype cycle. Like, we're in this kind of huge peak of inflated expectations around AI. There's a lot of myths out there at the moment. There's a lot of, the term AI and sometimes machine learning are used almost like punctuation in marketing materials. And it's because we're up here in this hype cycle. All of a sudden, everyone's an AI company. Everyone knows how to do machine learning. And I think it's incumbent on people like me who understand this to kind of help everyone else could understand the difference between the fact and the fiction. What's real, how is this technology transformative, and what is probably an inflated expectation. So hopefully over the next 40 minutes or so, you'll start to understand a little bit about what this technology is, where it can be applied, and what is probably more hype than reality. Okay. The other thing I'd say is that I think this is a great quote from Roy Amara. Roy Amara has a whole host of great quotes. But I think this is a particularly important one when it comes to things like machine learning. I think the same was true for big data and various other things. We tend to overestimate the effect of a technology in the short run. So people will talk about it suddenly transforming everything in the next couple of years. But we also tend to underestimate the effect of it in the long run, as in it becomes the kind of technology that fundamentally changes the way we go about life and how we go about day-to-day living. So this has been true about a lot of technologies. When computers first came out, there was a lot of hype about them changing everything, but really it took a little while. It really took almost a generational shift for it to change absolutely everyone's job. Right, the same has been true about big data as a specialization, and now a lot of the services that we use are fundamentally baked off, fundamentally built on this idea of connecting things at a large scale and making smart recommendations of things. So I think it's a particularly relevant quote when it comes to things like, when it comes to machine learning. I'm going to start right with basics. What is AI? This term AI is bandied around all over the place, and it's being, we're being told that it's going to, the savior of humanity, or maybe it'll steal all of our jobs and none of us will have jobs in 10 years' time. And there's a lot of kind of myth around this, but the term itself doesn't really mean much. It's never really meant much, even since it was first coined by an American back in the late 50s, early 60s, talked about artificial intelligence. It's never been formally defined. Artificial simply means something made by humans. And intelligence, well, we struggle to define intelligence even when it comes to humans. We have measurements like IQ and things, but they don't really sum up what we really think of as intelligence. So intelligence has never really been formally defined, even in the kind of animal kingdom. And so the term AI kind of has all of these kind of anthropomorphic kind of connotations, right? So when we think of AI, we think of like machines that are a bit human-like. I'd argue that's not what we want at all, right? I think we don't want machines to be like humans. We want machines to be like machines. That's what makes them give us superpowers. You don't want your thermostat suddenly getting bored of being a thermostat because it got really good at it and wanting a new job as a cooker. It would be terrible if that was how it was. Humans are terrible at a whole bunch of things. We get distracted. We start thinking about our pension when we're driving, and did I do the right thing with my investments, and all that horrible stuff that makes us amazing and general and creative and defines everything there is to be humans. But when it comes to machines, you don't really want machines to be like that. You want machines to be really good at a specific task and not get bored with them and all that other kind of stuff. So I think the term AI could be somewhat misleading, and it doesn't really mean very much. So it's always been a bit of a buzzword, always been a bit of a hype word. Today we're actually going to be speaking about a lot of the technology that's often used interchangeably with the term AI, which is something called machine learning. In order to get there, I want to talk about data and decisions and actions. There's a lot of talk. One of the biggest surprises I had when I first moved from finance into the glamorous world of media and advertising 4 years ago was how obsessed everyone was with data without necessarily understanding what it is. It's important to remember that data is only ever an observation of something that's already happened. You can kind of think of data as a photon hitting the retina of your eyeball. That's probably the best example of what data is. And data is often incomplete. You don't get to see everything. You can only see what's in front of you. Data is always stuff that's already happened. You kind of can't see into the future. And actually, most of the photons hitting the back of your eyeball are pretty useless most of the time, right? So this is all that data is. And now, don't get me wrong, data is phenomenally useful. Trying to play soccer or football with a blindfold on is a hell of a lot harder. You've got less data points, so you find it, close to impossible to do that. But by itself, data is pretty useless. It's noisy, it's incomplete, and it's always backward looking. The thing that matters to companies and to individuals are decisions and actions, right? It's like, what decision can I make? And often, way back when I used to advise large companies on things like data strategies, and they would embark on data lake projects or data warehouses and all that other kind of stuff, and they'd invest millions, tens of millions of dollars. I'd often advise them, before they started worrying about the data they need to collect, start with what decisions and actions do you need to take as a business. So start from that perspective. What decisions do you wish you could make smarter, faster? Are you structurally set up as an organization to make those decisions, even if you had and stuff? And when you define that, then you can work out, okay, what information do I wish I had to make these decisions faster and smarter? And often, a lot of companies are slowed down, not necessarily through a lack of data, but actually through organizational challenges of actually making decisions and turning them into actions. So I've often, with from my background, you might think it a little bit odd, but often I tell people to slow down a little bit on things like building large data platforms and start organizing and structuring themselves and working out what decisions and actions they need to take. But anyway, that's a bit of a soapbox moment. Today, I'm going to talk about what it is that connects data to smart decisions and action. What's this thing in the middle? And in the world of computers and physics and kind of mathematical reasoning, it's something that looks like this. The thing that connects data, observations about the real world that have already happened with some sort of decision and action. In the mathematical world or the computational world, are things like this. This is a mathematical model. this is a brilliant mathematical model for doing exactly one thing, and that's for drawing a straight line. This equation here, y equals mx plus c, allows me to draw this blue line here. Now, what do we mean by mathematical model? A mathematical model typically takes data points, observations from the real world, things that have already happened. These are the orange dots here. And a mathematical model allows me to draw this blue line through these orange dots. In this case, I've got age of fish on one axis here, length of fish on the other axis here. My orange dots are how I've measured different fish at different ages. I can fit, so-called fit my mathematical model, my y equals mx plus c, allows me to draw this blue line. Now that seems really simple, but that very basic concept allows me to do some pretty amazing things. That amazing concept allows me to do things like, if I don't know how old my fish is, I can simply measure my fish, and let's say it's 40 centimeters long, and I can look it up on the blue line, and I can see that it's 100 days old, right? It can also, if I want to work out how big my fish is gonna be in 20 days time, I can simply look up on this line here. These mathematical models allow us to understand, categorize, and predict the future, right? They do amazing things. This is the entirety of physics right here. The entirety of physics is this idea that I come up with some sort of mathematical model, something like y equals mx plus c, that helps me understand the real world, take real world data observations such as age of fish and length of fish, and then all of a sudden I can do these kind of seemingly magical things, like understand how old my fish is just from its length, or predict how much my fish is going to grow over the next 20 days. If you're massively into fish prediction, this would be an amazingly useful thing for you to do. But as I say, that's the entirety of physics. Since the dawn of physics and most of engineering is simply this idea. Come up with some sort of mathematical representation for the real world. This model is not perfect. It does not need to be perfect to be useful, but it does really help us with a whole host of different problems. So the problem with y equals mx plus c is that this is one model that's only good at one thing, which is drawing a straight line, right? And so the real world is very rarely this simple. It's very rare that you have these kind of relationships. Even if you're trying to do something like predict how much your house will sell for, you need to care about not only kind of fixtures and fittings in the house, and number of bedrooms, and where it is, and what street it is, what school catchment zone you're in. All of this kind of stuff, as well as what's happening in the wider markets and things, all impact the price of your house. So in reality, it's very rare that you end up with such a simple relationship like the age and length in the fish case. So what approach do you take there? Well, the approach that physicists take is something like this. You come up with more and more complicated and powerful mathematical models. So this here is actually an approach that was taken in financial markets. So when I worked in financial markets, this is what we did. We took the same approach as physicists, and there's a lot of physicists actually who work in financial markets, so they call themselves quants. I was one of these for a bit, and we would come up with we'd take that y equals mx plus c approach. We'd take the approach of trying to come up with more and more powerful and complicated formulas to represent, in this case, how stocks move over time, how volatile they are, how much they move up and down. And we have all these different parameters, such as interest rates and historical averages and all this other kind of stuff, which allows us to kind of predict something about, in that case, about the stock market. So this was the approach that we took in financial markets. We took the approach of physics and we applied it to how stocks and shares move over time. And this can work incredibly well, but there's a couple of challenges with it. The first challenge is that coming up with these types of mathematical models takes a lot of time. Right? It takes a lot of mathematicians' time to kind of hand crank these formulas and then to fit them to the real world. And this example took man decades to come up with. Right? This equation here took man decades to come up with. So that's the first problem. Very expensive to come up with, and you need a very specialist skill set to kind of come up with these mathematical models. The second challenge is that these models are only good as long as the kind of rules of nature stay the same. Right? Because we tend to fit these models to kind of historical observations because we don't know where to start. So we take all of our historical data points and we build mathematical models to represent our understanding of them. They're good as long as the rules of nature stay the same. Unfortunately, while that's true in physics, it's, you know, generally, as far as we understand it, the rules of nature don't change too often. When it comes to things like financial markets, this was no longer true. So when the financial crisis happened, for example, a lot of our mathematical models no longer held true. Overnight, it was almost as if our fish suddenly started shrinking and we didn't know anymore how old our fish were by being able to measure them. During the middle of the financial crisis, there were points where banks didn't know if they were liquid or not because they couldn't count, but because they were using mathematical models like this and trying to work out how long each fish was no longer held true. People were walking away from their houses even though there was equity in them. Interest rates were going negative in certain parts of the world. Various other things were happening, which fundamentally changed the broader context. And we didn't have the man decades it took to come up with this kind of formula to fit the new world. So first problem is that these models are very hard to come up with. The second thing is they're only good while your rules of nature stay the same. Now, if you were to try and try and take this kind of mathematical modeling approach and apply it to something as complex as human behavior, you're going to very quickly run into trouble. And the reason for that is human behavior changes. You can't account for all of the potential things that could, change human behavior, and it's changing dynamically all the time. So if you were to try and build a mathematical model, for example, for someone who's going to buy my product, something as simple as a celebrity tweeting about a garment or a new trend or a news report or things can kind of radically change consumer behavior. And if you had to go and hand crank a new formula every time, you're going to be in trouble. So fortunately, this is where this technology called machine learning comes in. So machine learning is this really simple idea. The machine learning idea is, wouldn't it be cool if machines could kind of understand the world and get better at problem solving by themselves? Wouldn't it be cool if they could learn how to solve problems by themselves? This is not a new idea. In fact, way back in the 1950s, Alan Turing, who is the grandfather of computer science, was in Manchester at the time at the University of Manchester. If you don't know about Alan Turing, thoroughly recommend. Fascinating character, fairly tragic ending. But Alan Turing absolutely shortened the war by several years through his work on code breaking, and he's absolutely the grandfather of a lot of modern computer science. Even way back in the 1950s, when the smallest computers in the world took up a massive room, they couldn't really do very much, and they were mechanical and they smelled, and it was kind of, that was what a computer was. Even way back then, Alan Turing recognized that one of the challenges of taking advantage of the computational age was going to be programming the computers, telling the computers exactly what to do. Even way back then, he talked about this idea, wouldn't it be good if a computer, bear in mind, computer, big mechanical thing back then, could organize itself to solve a problem, so that we didn't have to have these programmers who were going and setting all these knobs and dials and getting it to do exactly what to do. This idea of getting computers to organize themselves to solve problems is the same idea that we've been pursuing since the 1950s in this field called machine learning, which gives your computers the ability to learn without being explicitly programmed. The vast majority of software you use today, be it on your kind of cell phone or on your desktop or on your laptop, or even software that you're not even aware of because you're making a phone call and you're being connected automatically to somebody else. The vast majority of the software, somebody out there, a computer programmer has told it exactly what to do. For which I mean, when someone goes and presses this button, then go and do this other thing. Someone's kind of had the foresight to think, right, okay, this is the action I need it to take. If this, then do that. The vast majority of software does that. The idea behind machine learning is that computers can work out how to solve problems by themselves. Okay. So very, very simple idea, but how do you make that stellar leap from computers that do exactly what they're told to do because someone's had the foresight to program them, if this happens, then do this thing, to computers that can kind of learn and adapt to the world around them? How do you make that seemingly stellar leap? And we had this amazing idea back in the 1960s. This is a huge topic at the time. And it was based on a kind of understanding about a machine that we already had observation of that could take data from the outside world and process it and get better with experience. And we've all got one of these things. It's a brain, right? This is what a brain looks like. If you were to take your brain out of your head, put some dye in it and slice it very, very thinly. Don't do that. It's terminal. But if you were to do that, it looks like this pretty much all the way through. You've got these big black things here called neurons. They're connected to other ones of these neurons with these tentacly little things called synapses, and it's largely electrical, right? And at a microscopic level, the brain appears to be pretty simple, and it seems to be pretty consistent all the way through. Now, that's not completely true, but we tend to find this in nature all the time. Nature seems to work in a way by which you have kind of very simple mechanics at a microscopic level, So in this case, neurons and tentacly things that don't really do much by themselves, with the ingredients just right and applied at scale, and these magical things seem to happen. This seems to be how nature works. Same is true of things like evolution. So take evolution, the mechanics behind evolution are actually pretty simple. You've got, survival of the fittest, kill off the stuff that doesn't really work. You've got DNA, which allows you to pass on your traits to your offspring. You've got sexual reproduction, which allows you to take traits from two successful individuals and combine them and pass them down. And from all of that, you've got everything from flowers to humans, right? Just applied at a massive scale. The same, we see this pattern in nature all the time. Not complex at the microscopic level, but simple mechanics applied at scale. These magical things seem to emerge. The same seems to be true of brains. Simple properties at a microscopic level applied at massive scale, and everything that seems to be human seems to emerge from that. So there was this idea back in the 1960s, surely if we wanted a computer to be able to understand the real world, take in data and adapt and learn, surely all we had to do was copy the way that the brain works. Put one of these kind of things inside a computer chip, right? So this was an idea back in the 1960s. Today, this is by far the most popular way of achieving machine learning, achieving machines that are adaptable and can learn and get better with experience. It's to copy the way that we think, or a sort of crude approximation of how a brain works. Now, back in the 90s, if you hear terms like deep learning, artificial neural networks, all that other kind of stuff, that's all those terms mean. We've got a crude approximation of how we think the brain works, and we've shoved that inside a computer. Back in the 1960s, this was purely conceptual, but these days you can kind of get this stuff running in a web browser. So this here is an example of a brain, if you like, in a web browser. You've got inputs coming in here. This is kind of like the optic nerve. So the photons hit the retina of your eyeball. They send a signal down your optic nerve. That's your data here, kind of observing the outside world there. You've got this guy firing. It's like the synapse bits. This is a tentacle thing firing a little signal over here, over to a neuron. This is a kind of big black splodge. This is going to apply a function to the data it's got coming in, and he's going to fire it off to the next guy over here. Right. Now, it's worth noting that there is nothing complex in any of this. All these neurons are doing here is applying a mathematical transform function, a very, very simple function here. And the way that this computer is about to learn, the only thing that it's going to change is the signal going between these. So these lines here, it's going to make effectively that pipe fatter and thinner and positive and negative. The process of learning is simply updating what we call the weights. So how much to multiply this signal by when we get from this neuron to this neuron and this neuron to this neuron. And that's all learning really is when it comes to kind of machine learning. It's updating these little parameters here, lots of them. And we can quickly start that learning. And very quickly here, what we've got it to do is learn to differentiate, in this case, between blue dots and orange dots. So we started with some examples of blue dots and orange dots. And the process of machine learning took data about those dots and then adapted all these weights so it can come up with this understanding of a difference in blue dots and orange dots. Now, all it's really done there is draw a circle. The nice thing about this type of approach is that as my data changes, I don't have to go and hire a bunch of mathematicians. I can throw my mathematicians at the core problem of designing these, what we call neural networks, and then coming up with algorithms to adjust the weights to kind of process and learn so that my system doesn't have to have a new mathematician come in and come up with a new formula as data is changing. Now, if I try this more complicated example here, it's going to get a little bit stuck. This is actually mathematically quite hard to disentangle these blue dots and these orange dots here. And so you might think this is a bit rubbish, Peter. All you've done is draw a couple of circles and it got stuck as soon as I came across a hard problem. The nice thing about this approach is that I don't have to go back to the drawing board. I can just add a bunch more data and give it a little bit more brain power. So I don't know how much to do here, but we'll do this. And it might take a couple of minutes. But again, I'm not having to go hire physicists and mathematicians. This might take 3 or 4 minutes, but it will come up with some way of kind of building a brain that can differentiate, in this case, between blue dots or orange dots. So if something else were to come along and I had these data points about it, I can predict whether it's likely to be in the blue category or the orange category, right? If you hear terms like supervised learning, this is all that is meant by it. the vast majority of real world applications of machine learning today are essentially just this. Okay, they might be very deep, there might be a lot more connections in there, there might be billions of these neurons and things, but it's exactly this idea. It's take examples from the real world and train some sort of model like this to be able to understand them based on examples. So, even things like when I upload photos to Facebook, the fact that it kind of tags all my friends, it's because it's basically built these models to say, hey, that's a picture of my friend John. And it works well because John has uploaded and tagged himself in a bunch of photos. Say, hey, this is a picture of John, this is a picture of John, this is a picture of John. Okay, who's this a picture of? And we've trained one of these models to say, okay, that's John. Okay, so almost all the applications, the real world of applications of machine learning today are exactly this idea. I start with some examples. In this case, it was blue dots and orange dots. It could be spam email and not spam email. It can be picture of my friend John and picture of my friend Mary, that kind of stuff. We start with these examples, and what we're really doing is we're upping and down in these weights, in these more general models, rather than the Y equals mx plus c. We've got a much more complicated model here, and we spend all of our time as mathematicians coming up with decent kind of brain structures, if you like, doing what we call feature engineering, so making sure we've got enough input on this side, so we've got enough signal coming from our optic nerve, and then coming up with smart ways of then training, learning, which is making these pipes fatter and thinner. That's all machine learning really is. And I think often it's overhyped, and we tend to anthropomorphize things. So we tend to think of it as like these machines that are insanely clever. Don't be wrong, getting this stuff working in real life is still hard, but it's said like fundamentally it's not that complex. Okay, so congratulations, you now understand this topic called supervised learning. When I used to teach my master's level course in machine learning, it used to take at least the first semester to get to this point, but you're a very advanced class. That is all it really is to a large part of what we think of as machine learning today. As I say, this technology is very, very simple, but it has been transformative. It's been this technology that keeps your inbox free from spam, right? Way back in the 90s, I remember Microsoft, spam was such a problem with email that Microsoft was actually talking about charging people to send email. The idea being spammers wouldn't be able to afford to do that because it was just a really hard problem. Until machine learning came along, we could very quickly detect what's a spam email, what's not a spam email. And sometimes it's not sure. Sometimes stuff's on the cusp of between that blue dots and orange dots. So it'll actually surface to you in your email utility, your email application, hey, I think this is spam. Are you sure or not? Or is this what we call clutter now? And really what you're doing is you're giving it another training example of a blue dot or an orange dot. That blue dot and orange dot thing might appear really abstract, but as I say, it's what keeps your inbox free from spam. It's what detects faces in photos and then who those faces are of. Equally, it's what you do for things like behavioral targeting, right? So, blue dots and orange dots are people who bought a product. How can I build a model that can predict whether someone's in market for a product or not? I take exactly that kind of approach. So certainly everything we do at Quantcast, or a large part of what we do at Quantcast, is based on that same premise. Congratulations, team. We now understand supervised learning. I usually look for nods and smiles at this point to make sure people have understood it, but I can't do that in this weird Zoom world. So we're done, right? Surely all we need to do is get one of these neural networky things, plug them into all the world's problems, and all of a sudden we can all sit back and put our feet up and let the machines do the hard work. Unfortunately, this is not how we really learn, right? In the real world, if you think about the human experience of learning, it doesn't always work exactly like that, as in this is a picture of my friend John, this is a picture of my friend John, this is a picture of my friend John, who is this a picture of? There's certainly an element of learning like that, kind of this classroom kind of rote learning. But if we actually think about how people learn, it's a little bit more general than that. To give you an example of what I mean, this was a picture of my daughter Alice when she was, God, she must have been coming up for 2 here. She's 5 now and bizarrely gets harder work every week. She was going through a massive explosion of language around 2 years old, and I tested this on her at the time. She would say, hey Dad, what's that? And I'd say, it's a car. And she would know to apply that label to all of these images that objectively look nothing alike. If you were to tell a computer, hey, that's a car, and you showed it a picture of one of these other 2 things, it's not going to get it right, because if you look at it kind of pixel by pixel, these things look nothing alike. So how was she able to do that? Was she like particularly gifted 2-year-old? No, they can all do this. So that's a bit weird. Another example of what's a bit weird. if you read this sentence here, this is an example originally come up with by a guy called Jeff Hinton, who's one of the grandfathers of neural networks. If you look at this sentence here, she galuffed him with the frying pan. And I ask anybody what this word means here, galuffed, without thinking about it, everyone will say kind of hit or smacked or whacked. How is your brain able to do that? That's a bit weird, because that is a made up word. That word does not exist. And without any conscious thought, most people, even non-native English speakers, will think that word means hit or smacked or whacked. So, okay, maybe it's got an ED on the end. Maybe that means it kind of happened in the past. Galuffed probably doesn't phonetically sound particularly beautiful, so it's probably not a nice thing. So those could be reasons that we work out what it means. But actually, we think the most important thing is where it appears, as in where in the sentence. So what our brain's doing, our unconscious mind, is constantly trying to make sense of the world. If it doesn't understand what this means, it looks at everything around it. So she, and hit him with the frying pan, and thinks, what else could fill that gap? What else could fit in that space? And every other word that could potentially fit in that little point in space, it means hit or smacked or whacked or something like that. So this kind of understanding of the world, finding patterns in the world, is something that our human brains do incredibly well without someone saying, hey, this is the blue dot, this is an orange dot. This is the meaning of this word. This is the meaning of this word. Right? Somehow our brains are able to find patterns in the world, even for their own sake. And that seems to give us, the ability to learn at a massively accelerated rate. So this observation about how we think about language, about how our human brains process language, has led to huge transformations in the ability for computers to be able to understand language. So we took this observation, God, it must have been 15 years ago now, these kind of innovations happened, and whereby we said, well, look, could we get computers to understand language in the same way? What we mean by that is, can we kind of put every word at some position in space, and we'll move words that appear in the same context, as in words that would appear in this sentence, in this position in the sentence, move those close together, and move words that never appear in that same context, and as in could never appear in there, kind of further and further apart. And so that is the approach that we take, and it assigns a position in space to every word out there, and that gives us coordinates associated with every word. And from those, and as soon as you've got coordinates associated with something, some position in space, you've got the entirety of maths at your disposal. You can measure distances between words. When we started to do this, we'd take a large corpus of text, something like Wikipedia, and we would move words close together if they're in similar context, and far apart if they're never in similar context. That seemed to give the machine a really deep and rich understanding of language, because you can do things like take the word for king, as in the King of England, you can subtract the vector for man, you can add woman, and you end up somewhere near queen. Right, so it seems by finding patterns in the world and taking this kind of approach and applying coordinates to things like words, all of a sudden machines seem to get a general understanding of language, and it's that's allowed us to kind of supercharge things like automatic translation systems. So when you go into some system and say, would you like me to translate it from French to English for you? It can do that because machines have somehow got this understanding of each language itself, and then the job of mapping becomes a lot simpler. To make that a little bit more concrete, here's an example of exactly this, where every dot represents an individual web domain. So if I was to look at one of these dots here, that's, I don't even know what that one is. There'll be some odd ones out towards the edges. And every one of these dots is a web domain, and we can train models to tell us something about the web domain simply by how people move around the web. So you can kind of think about, as I move from one website to another website, the domains that I look at either side of one web domain tells me something about that domain, right? And so I can move it, and web domains that appear at a similar position, user journeys, as in surrounded by other similar websites, I can move really close together, and and web domains that never appear in that same user journey, I move further and further apart. So I can associate coordinates. Now, in reality, we use hundreds of dimensions to do this, to give us enough expressiveness in terms of positioning all these different things. So in reality, this model is 256 dimensions. Because our visual cortex can only handle 3 dimensions, we project it then down to 3 dimensions. And the job of machine learning is to effectively pull apart the kind of, in this case, web domains, and move them closer together or further apart based on them appearing in similar places in web domains. And its only job is to find, it's got no specific aim other than trying to find patterns, in this case in the internet. It'll take a couple of minutes to get going, but then I'm actually asking it to kind of make more sense of the world in 3 dimensions. And this is really the process of machine learning that you're seeing right here. It's iterating, it's going through multiple iterations of kind of pulling apart the world, trying to come up with slightly different adaptations of its model to be able to kind of make sense of it here. And so we're starting to see little clusters emerge here. I'm just going to pause that there. And so we can drill into this one here. This seems to be, I don't even know what that is. That seems to be kind of German type stuff. If we look into, there's a site I use quite a lot. I quite like cooking, so I use Epicurious. If I look at Epicurious, it seems to be in this part of space here. All the stuff that is close to Epicurious is all recipe sites, right? So there's a whole bunch of different recipe sites there. The only thing that we've used there, the computer at this point does not understand anything about recipes. It does not understand anything about cooking or audiences. All it understands is these web domains appear in similar positions in user web journeys, and I've associated this, I've associated position space with each of these web domains. I can do things like I can isolate, let's say, 600 of things closest to Epicurious. I could then find patterns here. In these, these are all vegetarian cookery stuff. Over here, we've kind of pretty got low carb cooking and so on and so forth. Again, this has not been based on anything like scanning the text pages or a fundamental understanding of different types of cookery. It's solely based on how users move around the web. Now, why is this useful? This is super useful because all of a sudden my computer has the ability to use these understandings, these general patterns of the world, and the same way my daughter could understand all these things are similar, like there's 3 different things of a picture of a car, then I can associate a label with that, and my daughter knows how to generalize that. In the same way, we understand language in a more general sense. The computers can use exactly the same approach. So I can do things like, rather than if I want to not show ads in a certain part of the web, rather than kind of blacklist whack-a-mole of these horrible sites that keep popping up, I can reframe that entire problem as, just don't hang around in that part of town. This area of space, don't show ads anywhere near those. Equally, if I'm selling a product and I'm trying to understand, okay, what is the behavior of people who are interested in my product, rather than finding an individual page or a domain or a URL, my computer can think of it as this area of space. So let's say a product that resonates with vegetarian cookers, and people are really into vegetarian cookery, my computer can say, this area of space is a kind of hot area. As someone wanders near this part of space, all of a sudden I think they're more likely to be in market for my product. Okay, so this idea of finding patterns in the world for their own sake, and then learning in that more generalized understanding of the world, is something we believe our human brain does incredibly well. And in machine learning, this is something called unsupervised learning. So we talked about supervised learning, starting with a bunch of examples, blue dots and orange dots, people who bought my product, didn't buy my product, spam, not spam. That's what we call supervised learning, as it's like supervised instruction, finding patterns and clusters in the real world with no specific example of what to label things. This is something called unsupervised learning. This is a big hot topic right now, and certainly something we're using a lot of to kind of supercharge our campaigns and make things like brand safety orders of magnitude simpler. And it's just based on finding patterns in the real world. You now understand unsupervised learning. That was year 2 of my postgraduate course and was all about unsupervised learning. And really, there's only really 3 forms of machine learning that we use. One is supervised, based on examples. One is unsupervised, find patterns in the world. And the third one is something called reinforcement learning, which is simply computers learning through practicing, playing computer games and things. So if you've got a world that you can simulate, then the computer can simply get better just by trial and error, getting better at it over time, or playing itself. Those are really the only 3 forms of machine learning that we have. Supervised, by example, unsupervised, find patterns in the world for their own sake almost, and reinforcement learning, just keep practicing, right? So that's all machine learning really is. It's this idea of copying the way that, or at least a large portion of it is actually copying the way we think a human brain works. It's taking data points, observations about the real world, and having more general mathematical models so we don't have to hand tune a model all the time. This has been fairly transformative in a number of different industries already. Things to watch out for when you start applying or being pitched this technology. I'm just making sure that I'm still on the thing.
We can see you. We can't see the deck, but I'd just like to remind everybody, we're going to go into the Q&A in a minute, so please do post some questions for Peter for the last 15 minutes. Back over to you, Peter.
Thank you. And okay, so finally, things to look out for if you are being pitched this type of technology. Number one, machines are ruthless optimizers that do not understand what you really mean. The biggest failure mode for applying technologies like this is to not be aware that all the machine is doing behind the scenes, all this clever AI technology, machine learning technology, is it is solving the exact problem as you set it. In order to do all this complicated learning thing, a machine needs a way of measuring whether it's getting better or worse, and it will ruthlessly optimize to do exactly what you tell it to do. So for example, if you tell a machine to optimize to something like a click-through rate, it will do it phenomenally well, and you will end up with a 90% click-through rate. That doesn't mean you suddenly found people who are desperate to click on ads. It means that you found bots. You might have even found a few toddlers in there, but it's not going to understand what you really mean. It's going to optimize towards exactly what you set it to do. It doesn't understand the broader context or anything. It's phenomenally efficient at optimizing, but it doesn't understand what you really mean. So the goals that you set it and the constraints you give it are absolutely essential. Otherwise, you can find yourself getting consequences that you didn't intend. Number two, the black box problem, as in understanding how it's working, is here to stay. And what I mean by that is people often ask, okay, but why? Or exactly how does that work? I cannot really tell you in this example how this neural network is differentiating between these blue dots and these orange dots, right? We often get accused as machine learning people, hey, it's just a black box. I don't understand how it's working. Unfortunately, what's happening is these mathematical models are only getting more complicated. They're very, very useful, but understanding exactly how they work is not a solved problem. All we can really do is understand what these kind of models are sensitive to, so we can kind of put them in a jar and throw different things at them. We can see how they adapt and change over time, but actually understanding exactly how they work is not a solved problem, and so that's kind of here to stay. And the third thing I would advise you all, as you're probably being pitched machine learning and AI technology, is beware anything that appears it's magic. A lot of this the fundamentals behind this technology are actually pretty simple. There's nothing kind of magical in there. Beware this being pitched, hey, it's AI, it's just AI, it just does this, it's just magic. I've heard a lot of pitches these days which make you think, these people don't know what the hell they're talking about. So hopefully you understand a little bit more now about what this technology is behind the scenes. It's not nearly as daunting or scary as it is often pitched to be. It is not nearly as human-like intelligence as often a lot of popular press turns it out to be. It's actually a simple set of techniques kind of applied at scale. I do believe it's transformative. I do believe that it's already changed our world. I think it will continue to change our world, but it's not human-like intelligence. So with that said, thank you very much. I'm going to open it up to questions.
Thank you, Peter. First question I've got from Tom. Are the machines able to distinguish between causation and correlation? E.g., when finding patterns, is there a danger of pursuing red herrings?
Absolutely, that's a massive danger. I mean, this is true of everything. A lot of the work that you actually do in machine learning is less to do with the kind of structure of the neural networks and the algorithms. Actually, more to do with making sure that you're giving the right examples, making sure that you're constructing things in a way that you're kind of engineering your true and your false sets effectively. The only real way of establishing causation is through double-blind tests. This is true across science. It's not unique to marketing. So to do what we call in marketing an A/B test, a properly robust A/B test where you reduce bias and everything else, it's the only way of establishing causation. There is no other way. If someone's told you that they can do it via multi-touch attribution, I would love to debate that person. The only real way of establishing causal relationships in any field of science is through double-blind tests. And just like anything else that you're fitting, of course, you can mistake correlation with causation. So you have to be really smart about what you're optimizing for, as in how you state your problem to a machine that is optimizing towards it. And you need to be really careful about the examples you're giving it. and how you sample your examples and various other things have a direct impact. But ultimately, the only way of really establishing causation is through then running a series of A/B tests.
Thank you. Slightly off topic from Taran, but a big topic, so to speak, a very big topic. I'd like to ask Peter how cookie blocking on browsers such as Safari and Chrome will impact technologies such as Quantcast. Will there be a way for us as marketers to target individuals in the way that we're able to do now?
Yeah, I talk a lot about cookies at the moment. Yeah, I think it's gonna change things. I mean, I think the first thing I'd say about cookies is that they're not nearly as persistent and durable as people think they are. You know, almost half of web traffic today already has no cookie associated with it. So it's already pretty broken. And this is, you know, the recent Chrome announcements and things have only, you know, they're just the final nail in the coffin. I think ultimately, yeah, I mean, we've been investing in this area for a long time, as you might imagine. There's two approaches you can take. One is to come up with long-lived identifiers, things like email addresses and various other things, which allow us to have that longitudinal kind of analysis of users over time. We'd like to see a few things emerge there. So, you know, you'll start seeing some announcements from us fairly soon on that. We're not ready to talk about it just yet. The other thing that we're starting to see is applying these machine learning approaches to being able to correlate things together between different sites. So it's actually relatively easy as long as it doesn't need to be deterministic. If you can say, take a probabilistic approach, and you can be 99.5% certain that it's the same individual moving between different websites. As long as you bear that probability in mind when you're aggregating your numbers, you can still get decent measurement. And as long as you've got decent measurement, you can optimize. Right, so there's a big misconception, I think, when it comes to the challenge with cookies going away. A lot of people think about it in terms of targeting. I'd actually argue the first thing that needs to be solved is measurement. But already we've had huge advances in how we can measure without cookies, because we've had to do it on Safari for a number of years now. And it does mean that marketers are going to have to get used to different types of techniques. They're going to have to get used to probabilistic methods of measurement and looking at cohorts of numbers rather than reducing everything to a single measure. I think that's something that needs to happen anyway. I think a lot of the numbers that are used today are actually a little bit misleading. But yeah, so I think it will change things, but I don't think it's going to be as dramatic as some people are kind of calling out. The first problem to solve is actually measurement rather than targeting. And how do you measure in a cookieless world? And certainly we've been piloting with a number of brands over the last 18 months now, different ways of doing that. And we got our next pilot program launching in September. I think some people on the call might even be on that round, and another pilot round launching in December, another one in February. For how do you solve the measurement problem with ITP traffic? Because that's the best proxy we have for how the entire web's going to look in a few years' time.
Okay.
So yeah.
Okay, I want to cut in there, Peter, because there's two more questions, and I will just like to say that we'll be emailing everybody on this webinar, and there's an email address that you can email further questions to, and we'll get back to you and answers. Okay, just a couple more with the time we have left, Peter. What extent can we train the machines to make smarter decisions? In your CTR example, how would you go about making sure it gets a strong CTR from more desirable users and not just bots, etc.?
It's all to do with how you measure success. Like everything that you need to do with machine learning, as a lot of engineering, it's about stating the problem really well. So it's a lot more effective, for example, to optimize towards conversions than it is to optimize towards click-through rate, right? Because, you know, bots don't have credit cards. So if you have a conversion inside of a credit card board, if you optimize towards that event, then that's actually related to the value that a business gets from it. So what you choose to optimize for is really, really important, and putting constraints on that. So it's all about how you state the problem. It's all to do with what you're optimizing for. A lot of people, I think this is true across everything, right? Your measurement directly dictates behavior. Now, machines are much more ruthless at optimizing, but I'd argue that everything that is measured and has some sort of economic advantage when you measure it, ultimately dictates behavior. Economic systems adapt to how they're measured constantly. Really good example, like when everyone got obsessed with viewability a few years ago, they turned that measurement into a target, which is something you should never do. And they said, look, we want 70% of our ads to be viewed. So people who took an approach like us, of course, you can hit that because your machine can learn where the viewable inventory is. But over time, actually, the entire web adapts. And so all the participants in that economic system, all of a sudden publishers are putting all the ads at the top of the page to get high viewability scores. They're lazy loading ads, so that they only show when you hit a certain point in the page to hit that viewability metric. Right now, so ultimately, how you measure things dictates behavior of wider economic systems, and machine learning is just much more ruthless at kind of finding optimization. But to kind of actually get kind of incremental growth and things, is all to do with how you measure. Everything comes down to how you measure it. And so, yeah, you can't say just good clicks. You need to be able to say, okay, I care about a conversion rate at this amount, and I'd love to achieve a CTR at this level. Is probably the best way to state that problem. Click-through conversions themselves are often too rare to be able to train models on. So you tend to have to use proxies when you start building these models for things like click-through engage, and overlay that with an engagement to conversion model and various other things.
Thank you. And now this question. Hi, Peter. Thank you. That was great. You made it very clear and simple to understand. Do you think some advertisers are hesitant to engage in programmatic advertising due to a lack of knowledge on the topic? And what can we do as an industry to reverse this? Well, I guess this webinar is one way of helping to clarify that.
I think as unfortunately what's happened in the programmatic ecosystem is there's been a lot of money spent on hype. You know, this tends to happen when a lot of VC money in particular gets applied to a certain industry. Almost the first thing that any tech company does is hire the marketing people and to drum up some business. And so there's been a lot of hype in this space for a long time. And I think probably in programmatic, we spend too much time too much time talking about all these technical complex things and not nearly enough talking about marketing challenges. Like, unfortunately, what's happened in the programmatic ecosystem is it's just got more and more complex over time, and it's become more and more divorced from being able to speak to marketers in terms of marketing challenges, which is understanding, reaching, and influencing audiences. And how can I use this technology to help me achieve getting this message out in front of people and seeing if it works or not? You know, one of the beautiful things about the digital world, one of the huge advantages that it gives us, it's fundamentally transformed how we think about business, is the fact that we can test and learn much more easily. The fact that we can roll out things and we haven't got to build an entire assembly line. And if I make a mistake, I can kind of roll it back and I can run it on a subset of my audience. Doing that kind of stuff today and taking advantage of that from marketers is just too hard. So actually, I don't think the problem is with a lack of education about how the nuances of programmatic work. I think as we have not done a good enough job at speaking in marketing language and enabling marketers to do the marketing job, which is to understand value propositions, push them out there to specific audiences, you know, hitting that audience and seeing if it works or not, and being able to test and learn with marketing ideas rather than bid tactics. I think that needs to be where programmatic goes, because programmatic is just a means to an end. It's just about allowing marketers to get their message out there in front of an audience and seeing if it works or not, and then adapting. And I think too much time also is spent in the weeds of parameter tweaking, and not nearly enough time has been spent actually reframing it as a marketing opportunity. I think this is one of the reasons why I think things like Facebook do incredibly well. They hide all of the complexity. The Facebook Ads Manager is anyone can use it as a marketer, and you can test and learn really easily. And generally, it kind of does what you expect. Whereas programmatic can just be a lot harder. The barrier to entry is too high. So I think my view is that it's less about educating marketers on the nuances of programmatic. It's more about reframing some of the things that are available in the programmatic ecosystem to solve marketing challenges.
That's a really interesting answer. Thank you, Peter. And on that note, I think I'm going to draw things to a conclusion today. If you have any questions, please feel free to email us at innovate@quantcast.com, and we'll also post a recording of this to everybody who attended the webinar. So please look for that email. And we look forward to seeing you at the next session. And good morning, Peter, and good afternoon, everybody else. Thank you.
And apologies, everyone, for my tech issues.
Yeah, never mind. Cheers. Thank you.